Hello. Today I'd like to talk about space optics fundamentals with a focus on weather. This presentation goes over the fundamentals of the science behind what we do here in Fort Wayne, Indiana at L3 Harris Technologies. And our present today will kind of be just a larger overview of how these principles work. So a little bit about me. My name is Martin Kwong, and I'm a project engineer on the GeoXO sensor unit, which will house the GXI, the next generation, the successor to the Advanced Baseline Imager. Here's my background education. I have a bachelor's in oceanography from the United States Naval Academy. I have an MBA from the Cornell Johnson Graduate School of Management, and I have a master's in space systems engineering from the Johns Hopkins Whiting School of Engineering, with a focus on electro-optical space systems and propulsion. So, what is light? The definition that I was able to find from the Encyclopedia Britannica is light is electromagnetic radiation that can be detected by the human eye. Now, this is an incomplete definition because electromagnetic radiation occurs over an extremely wide range of wavelengths, from gamma rays, high energy rays, to radio waves, lower energy. Most of these are invisible to our unaided eye. You can see here you have this spectrum, this EM spectrum, gamma rays, the higher energy, radio waves, the lower energy. This very narrow band right here is where visible light lies, and these are the colors that we see from, think of Roy G. Biv or the rainbow. You have your violet, and then you have your red. The violets have the shorter wavelengths, the higher energy, and the reds have the longer wavelengths, the shorter energy. So this is demonstrated with a prism, right? So visible white light is made of many bands of light. It's not a color onto itself. It's actually all the bands of light put together, of visible light put together. So you see the prism, the white light beam enters in. It goes through refraction, the light property, and what comes out are your colors right here. And as you see from this EM chart for visible light, you have 750 frequency, where your 750 is here on the very far left, and then the very far right is a 380. So as you can see, frequency is higher on the violet and red is lower. The wavelength is the inverse relationship. The wavelength is shorter for the violet and longer on the red. And this is the spectrum, the continuum that shows the relationship. And here you have photon energy in terms of electron volts. We compare photon energy to electrons because of an interaction, which we'll get into a little later. A fun fact, a laser is a single wavelength of light. So if you have a red laser, it's actually, it's an individual band here, and it won't refract. So if you put it in this prism, it'll come out as red. So continued, what is light? Light is a wave, right? So we first discovered that light is a wave. And this was done through an experiment called a double slit experiment, where a beam of light was shown through two slits simultaneously. And then what came out was an interference pattern. This here illustrates what happens between those two slits and the backing of the wall. You have these ripples, like a wave. If you imagine if you throw two rocks together, two rocks, one rock here, one rock here, they would create ripples. And these ripples then constructively and destructively interfere, which then gives a fringe pattern on the wall. And this is actually done with a red laser. I have some examples here. So the top one is the one that I made myself at home. I actually shined a red laser, let it get split by a strand of hair, and what was result was a fringe pattern on the wall, which shows the constructive and destructive interference. Here's a capture from a video where someone actually put a strand of hair in the middle, split a green laser. The same thing happened. And then here is from a YouTube video, shows the mid-flight pattern, the wave, the ripples, the constructive and destructive interference happening mid-flight. So continue with what is light. Light is a particle. The fundamental particle of light are photons. So mentioned earlier about photons and electrons, their interaction. So we first figured out that light was a particle from the photoelectric effect, phenomenon in which electrically charged particles are released from or within a material when it absorbs electromagnetic radiation. Here you can see the photons enter and they hit electrons on the material, and electrons are released. And what happens is that when the electrons are released, they cause a current. This current can be captured and digitalized. And that's the fundamental process of how cameras work. So this gets into the duality of light. So light is wave-like and particle-like. Well, the particles themselves are particle and wave-like, right? That's fundamental. And so light behaves like a wave and as particles and works in a probabilistic nature. We do not know, right, where the photon is until we try to observe it or measure it, and then it collapses into its state. The act of measurement slash observation changes the behavior of light. This has a lot of implications for the nature of reality. And here we have an example where when you send photons through two slits and you do not try to measure them, they create the wave pattern, the wave interference pattern. However, when we send individual photons through each left or right slit, and we have a which way device, a device that measures which way it went, it actually collapses the wave function into left and right. And if you were to send individual photons through these slits and not measure them, not measure which way, they would actually collectively create this wave interference pattern. The study of this is referred to as quantum mechanics. And there's many different explanations for why this phenomenon happens. You can look into the terms, but it comes down to, do you subscribe to a deterministic or non-deterministic universe? Does the act of measurement of observation break down the probability of the nature of matter, the nature of reality? Interesting thing to note is that it's not just photons and other particles like electrons that are on the standard model. They actually are able to do this with atoms and molecules up to a certain size. Beyond a certain size, quantum mechanics stops really being the physical explanation, and then we get into the larger state of matter of which is governed by general relativity. So when people talk about the theory of everything, they're talking about a theory that would connect both of these, quantum mechanics and general relativity, which would be a very groundbreaking thing and something that's been worked on for decades. So photon capture, right? Photons to electrons to signal to data. Here we have a filter of red, green, blue. So when light comes in through your lens on your phone, it goes through this screen, which which then filters down the light to red, green, or blue. And then those strike a sensor, which is where the photoelectric effect occurs. The sensor has pixels. The pixels have electrons on them, and that knocking off those electrons creates creates a current, which then is converted to digital information. And you can see here, you have these fruit, the basket of fruit, goes through the lens, hits the red, green, blue filter, hits the sensor, and then you have a process of analog to digital conversion until you get to your phone storage. In this case, it's SD card, but internal storage. And that's how your phone captures images. And this all happens very quickly when you snap the button. So why is this all important, right? So optical engineering is the engineering that is used, that governs this, and is used in all kinds of things we use every day, from our TV remote to high-speed fiber optic cables for high-speed internet, and is also very important for Earth climate observation. Water vapor, clouds, wildfires, hurricanes give off energy. They give off a lot of light energy in the form of infrared, which is heat energy. Infrared light is a type of radiant energy that is invisible to human eyes, but we can feel as heat. With optical instruments, we can observe and map infrared light to track weather. And here's an example of one of those maps. So also, why space, right? Why is this space optics fundamentals? The further away you are from something, the more of it you can see. Geostationary operational environmental satellite GOES is the current generation of geostationary satellites that are in orbit right now, which have the advanced baseline imager. Geostationary orbit is a circular orbit 22,236 miles above Earth's equator, in which a satellite's orbit is equal to Earth's rotation. So the spacecraft is stationary relative to Earth. As Earth is rotating, the spacecraft is orbiting at the same rate of that rotation. And here's a current generation of fleet. Most recent is GOES-U, which is GOES 19 now since it's on orbit. And here's a history quickly of GOES. You look at 1975 to now, there's been some marketed improvements. I would say the big generation gap is going from what was basically a camera in space, a broadcast camera, to a multispectral imager, something that can go from 400 nanometers or zero point 0.4 microns to 14 microns in 16 channels. And that just allows us to capture and map data far beyond what our eyes can see. Here's our fleet. So you have on the far outside ring, we have our fleet of GOES satellites. And then a couple other satellites, so low Earth orbit, like a polar orbit here, that goes North Pole, South Pole, and the Earth rotates under it. And then, yep, just shows just different fleets that are out there. So some optical engineering fundamentals. So a mirror, a beam splitter, and a light filter. A telescope focuses light to a focal point. A mirror reflects light based on incident angle. So the angle it comes in is equal to the angle it exits. A beam splitter splits a light beam into separate beams. You can see here the green laser through this cube beam splitter is split into multiple beams. An absorption filter only lets specific wavelengths of light pass through, blocking all other wavelengths. You can see this example of all these colors coming in and only allowing green light to come through. The 520 stands for 520 nanometers, which is that wavelength. And I have some optical demonstrations, so I did this in my own little at-home optical lab. So a pen light, a white light source, is focused down and fed through a cube beam splitter, which splits the light, and then is fed through two filters, right? So you have this path and this path. This is a long pass filter from 400 nanometers to 600 nanometers, which transmits the 400 nanometer to 600 nanometer beam of light, and then it hits a 400 to 500, so it's even more specific, and then transmits the 400 nanometer to 500 nanometer light into a focal point right here. In this case, you have a 570 nanometer or 780 nanometer optical filter that allows that transmission. And then a 660 to 780, which is very much in the red area, which then transmits red light. I'd like you to notice that the violet in this case is higher energy, right, which is shown here, much more visible, and the red is lower energy. So that kind of shows that there's this photon energy effect, and you have a reflection, right? So these are actually mirrored surfaces, slightly mirrored, so there is a reflection. It comes in. These are tilted at 45 degrees roughly, so the beam comes off at 45 degrees. Also, note there's stray light here, right? And this might be exacerbated by the fog machine, but the stray light shows the challenges in optical engineering. I mean, this whole thing shows you have reflection, you have multiple beam splits. These are all challenges that must be overcome in optical engineering in order to get truly the wavelength that you are looking for, the band of light you're looking for. Here's an example of transmitted light with the narrow filters up front placed first. So in this case, light is filtered to 400 to 500 nanometers, and it passes through the 400 to 600 nanometer filter, and it stays its characteristic bands. So it's already filtered down. Here, it passes through the 660 nanometer, 780 nanometer, and it stays 660 to 780 nanometers and passes through this longer optical filter but stays red. Here's an example of no transmittance. This is an example where we swap the long pass filters. So this one is 570 to 780 nanometers. And what happens is because the light is not does not match this optical filter of 400 nanometer to 500, right? If this goes to 500, this starts at 570. There's no transmittance, with the exception of some stray light. Engineering challenge. In this case, 400 nanometer, 600 nanometer optical filter allows that wavelength to transmit, and then your optical filter 660 to 780, because there's a gap, right? There's no transmittance. Here's an example of when we swap the order and there's no transmittance, but we start off filtered down more narrowly. This is 400 nanometer, 500 nanometer optical filter. Lets that band of light through. But this optical filter, this long pass, is 570 to 780, so it doesn't go through either. And then in this case, this optical filter is 660 to 780, which transmits that light, and it's really hard to see because it's very red, a low photon energy. And an optical filter here, 400 nanometer, 600 nanometer, doesn't match up. It's outside the range of this, so there's no transmittance. So with that said, then we get into our current generation on-orbit imager, which is the Advanced Baseline Imager. Here's a picture of one of the GOES satellites, and the Advanced Baseline Imager is right here. And this is what it looks like as a standalone unit. Here it shows the wavelengths of light that it collects: visible near infrared, mid-wave infrared, long-wave infrared. So it captures this visible band, but goes all the way into the infrared bands. And then you have some optical elements here. The basics are light is fed through a telescope, and then it's fed through these optical elements. It's fed through mirrors and beam splitters. And then it hits your visible near infrared, mid-wave, and long-wave infrared filters and sensors. And here you have these bands, which are in microns. So from 0.47 to 13.3. All that then creates this image, a scanned image, which is then, we can break that down even further into color coding for the infrared channels. The more applications of infrared optics. So James Webb Telescope, deep space exploration and observation. Here we have it with the gold mirrors. Our company actually was part of the design of these gold mirrors. And Hubble to James Webb, as you can see, there's much more clarity and also detail. The Nancy Roman Grace Telescope, which is tentatively scheduled for 2027 to be launched, will focus on some phenomenon like supermassive black hole collisions, dark energy, and dark matter. And here's a little illustration of that. And two black holes colliding. And why are these interested in infrared, right? That band of light. It's due to redshift. So the displacement of the spectrum of an astronomical object toward the longer red wavelengths. It's a type of Doppler effect where as things move further away, light travels, and the wavelengths get longer and longer as they lose energy. And so if something is maybe blue at source, by the time it gets to your eyes, if it's far away, it might actually be infrared. So infrared optic can then detect it, and then we can add the color in ourselves. And here's a video of a launch of GOES-U, which is now GOES 19. I was here to take this video.